Students, now we are starting the lecture 2 of our unit 3, Elasticity. Now in this lecture, before I start the lecture 2, let me just give a recap of the lecture 1. In lecture 1, we learned how to notate the various components of stress, then when to take them as positive, when to take them as negative. Remember, normal stress is positive if the stress creates a tension in the body. If it creates a compression, normal stress is negative. Shearing stress, notated as tau, can be taken as positive if the tensile stress is in the direction of the positive axis. The diagram shown, you can see the various components of stress, both normal as well as shearing stresses on various faces of this cube. We also learned in lecture 1 the various components of strain, the normal and the shearing strain. Normal strain is notated as epsilon, shearing strain gamma. So there are 6 components of stress and 6 components of strain. Now starting our lecture 2, let me first define Hooke's law, named after Robert Hooke. So every body has a limit called elastic limit, within which stress is directly proportional to strain. So stress by strain is equal to a constant called modulus of elasticity. And another important definition before I proceed to the subject is Poisson's ratio, notated as nu. The ratio of the lateral contractional strain caused by any stress to the longitudinal extensional strain for the same stress is known as Poisson's ratio, nu. Students, you can see in this diagram, trying to stretch a band. So there is a longitudinal strain. Simultaneously, for the stress applied, there is a lateral contractional strain. So this ratio, lateral contractional strain to the longitudinal extensional strain, is called Poisson's ratio. Now let us learn to express the generalized Hooke's law. Now pay attention to this diagram. We have an elemental rectangular parallelepiped structure with the sides parallel to the coordinate axis and submitted to the action of normal stress sigma x, uniformly distributed over the two opposite sides. Now from Hooke's law, we know that stress by strain is equal to a constant called modulus of elasticity. So let me express now the stress sigma x by the strain epsilon x is equal to capital E. Remember, E is called Young's modulus. So from this equation, I can express the extensional strain in x direction, epsilon x is equal to sigma x by E. Now this extension of the element in x direction is accompanied by lateral contractional strain components in y and z directions. So whenever I try to extend a body along x direction, there is a contraction in y direction as well as z direction. So from the definition of Poisson's ratio, we have lateral contractional strain is equal to Poisson's ratio nu into extensional strain. So now I can write the contractional strain in y direction as minus nu into sigma x by E. Similarly, the contractional strain in z direction as minus nu into sigma x by E. Both are same. This negative sign indicates the contraction. So whenever there is extension in one direction, there is a contraction in the other two mutually perpendicular directions. If the extensional strain in y direction due to sigma y is epsilon y is equal to sigma y by E, capital E, then the contractional strain in x direction is minus nu into sigma y by E, as well in z direction is minus nu into sigma y by E. So this is the extensional strain due to sigma y, and these are the contractional strains in x and z directions. Also, the extensional strain in z direction sigma z is epsilon z is equal to sigma z by E. So again, the contractional strain in x direction and y direction is minus nu into sigma z by E. Nu stands for Poisson's ratio. So if the element is subjected simultaneously to the action of normal stresses sigma x, sigma y and sigma z, so this is sigma x, sigma y, sigma z, and uniformly distributed over the sides, then superposing the strain components produced by each of these three stresses, we obtain the resultant strain components as epsilon x is equal to 1 by E into sigma x minus nu into sigma y plus sigma z. From the equations in the previous slides, you can understand this is the resultant strain in x direction. Similarly, the resultant strain in y direction. So the first part is indicating the extension, the other two the contractions. Similarly, epsilon z, the resultant strain in z direction. This is again, this part is extension and then followed by the two contractions. So this very thing is what we call generalized Hooke's law. Let us label these equations as equation 3. Now we will try to obtain the relation between various elastic constants. Just now we derived generalized Hooke's law. So the resultant linear strain in the direction of x can be expressed as epsilon x is equal to 1 by E into sigma x minus nu into sigma y plus sigma z. We named this as equation 3 in our previous slide. Here capital E is Young's modulus or modulus of elasticity in tension. Now let us consider case 1. where sigma y is equal to sigma z is equal to 0. Substituting this in this equation 3, we have the resultant strain epsilon x is equal to sigma x by capital E. Let us call this as equation 4. Now consider the case 2 where sigma x is equal to minus sigma y and sigma z is equal to 0. In the sense, there are two stresses, two normal stresses. Both are equal in magnitude, but one is a compressive one, the other one is creating a tension. Substituting the above condition in equation 3, we have the resultant linear strain epsilon x is equal to sigma x by E into 1 plus nu. And again, we have an important relation. Shearing strain is equal to 2 times linear strain. Linear strain or normal strain, both mean the same. So shearing strain is equal to 2 times linear strain. The derivation is not included in this presentation, but we can always show that shearing strain is always equal to 2 times linear strain. So in place of linear strain, let me write this sigma x by E into 1 plus nu. And now let me express the Hooke's law. Shearing stress by shearing strain is equal to sigma x into capital E by 2 sigma x into 1 plus nu. Remember, even though two stresses are being applied, their magnitude is same, equal to sigma x. So it's enough I express the magnitude here, sigma x into capital E by 2 sigma x into 1 plus nu. That gives us a constant notated as capital G. Here from this equation, G is equal to E by 2 into 1 plus nu. G is called as modulus of elasticity in rigidity, or simply rigidity modulus. Let us name this as equation 5. So until now, two different moduli of elasticity are defined. One is Young's modulus, notated as E. The other one is rigidity modulus, notated as G. Now let us consider the case 3, where there are three normal stresses acting in three mutually perpendicular directions, x, y, z. Let us take the case where they are equal in magnitude. Sigma x is equal to sigma y is equal to sigma z. Now let us again substitute the above condition in equation 3. Epsilon x is equal to 1 by E into sigma x minus nu into sigma y plus sigma z. Then we get the resultant linear strain as epsilon x is equal to sigma x by capital E into 1 minus 2 nu. Now, just like shearing strain is twice linear strain, we can also show volume strain is equal to 3 times linear strain. Now, even this derivation is not included in this current presentation. Now, in place of this linear strain, let me substitute sigma x by E into 1 minus 2 nu. So now again, let us take the ratio of stress to strain. Now it is volume stress to volume strain. So that is equal to volume stress is sigma x, volume strain 3 into sigma x into 1 minus 2 nu by E. Now, so E goes to the numerator. Now, this is a constant again, K. Stress by strain is a constant as per Hooke's law. So now this ratio is now again a constant equal to K, where that K is equal to capital E by 3 into 1 minus 2 nu is called bulk modulus or modulus of volume expansion. So with this we defined totally 3 moduli of elasticity. The first one is Young's modulus E, second one rigidity modulus G. Now this is the third one called bulk modulus K. Now from equation 5 in our previous slide, we can express 2 plus 2 nu is equal to E by G. Remember students, for better understanding of this derivation, you take a parallel running notes or derive along with this presentation so that you don't get confused. Now, from equation 5 in the previous slide, we have 2 plus 2 nu is equal to E by G. Call this as equation 7. Now, from equation 6, we have 1 minus 2 nu is equal to E by 3K. Call this as equation 8. So let us add equation 7 and equation 8. We are left with 3 is equal to E by G plus E by 3K, or putting it in a proper manner, E is equal to 9GK by 3K plus G. This is a very important relation, the relation between the various moduli of elasticity E, G and K. So now students, we are about to learn the elastic behavior of a material under increasing load. I am trying to show you the stress-strain diagram. So let us consider a body subjected to a uniformly increasing stress, which results in a change in its dimension. So the corresponding stress-strain curve is as shown. Remember, strain is taken on x-axis, stress on y-axis. The graph is something like this. Now in the region OA, you see it's a straight line. In the sense, stress is proportional to strain. That is, Hooke's law is perfectly obeyed. So this up to the point A, where Hooke's law is perfectly obeyed, we call this point A as proportionality limit. Now in the region A to B, stress and strain are not proportional. You can see it's not a straight line here. Stress and strain are not proportional, but the body returns to its original dimension when the stress is made 0. Now this very point B is called elastic limit. So between A and B, though Hooke's law is not obeyed, the body is still elastic in nature. Now this point B is also called as yield point. Now when I increase the stress further, strain increases very rapidly, even for a small change in stress. Now in between the point B and D, When I remove the load, say imagine at the point C, if the load is removed, you can clearly see the strain is not 0. So the curve won't take the path back to O, rather there is some permanent strain left over, what we call it as permanent set. So the material is said to have permanent set. Now let us consider the point D in the graph, which is called ultimate tensile strength of the material. Ultimate tensile strength. Beyond this point, an additional strain is produced even by reduced applied force. Now even if we reduce the force, the applied force, still the strain continues, and finally there is a fracture at the point E. So this point E is called as fracture point. Now in this graph, if the distance between D and E is close, so the points D and E are very close for some material, you say the material is brittle, just like the glass. Now if they are far apart, the material is ductile. Students, this is an important short answer question for your examination. You have to show this graph and explain all the various points or the stages a wire or a body under increasing load passes before it reaches the fracture point. With this, I am trying to conclude my lecture 2 on elasticity. Now, at the end of this lecture, you should be in the position to answer the following questions. You should be knowing how to express the generalized Hooke's law. What is the relation between Young's modulus, rigidity modulus, and Poisson's ratio? What is the relation between Young's modulus, bulk modulus, and Poisson's ratio? What is the relation between the three kinds of moduli of elasticity, E, G, and K? Also, you should be in a position now to explain the behavior of a wire under increasing load. Thank you.